Every day, tens of millions of Americans cross bridges rated in poor condition without giving it a second thought. Across more than 600,000 structures, the average age has hit 47 years, with entire fleets built during one post-war boom now deteriorating together. This isn't simply about old concrete. The deeper question is why wealthy nations keep deferring the one investment that would cost the least. A bridge is rarely noticed until it stops working. In daily life, these structures act as physical links in highly optimized networks. A morning commute, a municipal fire department's dispatch route, and a grocery store delivery schedule all depend on these spans. Every day, commuters cross these structures to reach jobs, schools, and medical centers, expecting the roadway to remain open and stable. When one crossing is weight-restricted or closed, the ripple effects spread immediately. Freight dispatchers must reroute trucks, adding miles to shipping corridors that connect maritime terminals with regional warehouses and manufacturing plants. Just-in-time delivery systems rely on predictable transit times, meaning a single detour can disrupt assembly lines hundreds of miles away. In residential areas, emergency services rely on these crossings to maintain rapid response times. When a local bridge is restricted, a fire truck or ambulance must take a long bypass, turning an urgent rescue into a delayed arrival. These structures function as the physical connectors holding industrial corridors, public safety networks, and daily commerce together. If one link fails, the entire regional system slows down. The current strain on this network is not random, nor is it limited to a few neglected spans. It is a predictable consequence of timing. The average highway bridge in the United States is 47 years old, with the vast majority built during the post-war construction boom of the 1950s, 1960s, and 1970s. Designed with an estimated service life of approximately 50 years, this entire generation of steel and concrete is reaching advanced age at the exact same time. This infrastructure demography is a global phenomenon. In Canada, 42% of public bridges were built before 1990. In Germany, 38% of the inventory dates to before 1970. 45% of the United Kingdom's major road bridges are older than 40 years, while Japan and Australia see 46% and 40% of their fleets exceeding these half-century and 40-year baselines. When a society builds its core networks in a single concentrated burst, it inherits a synchronized expiration date. Across these developed nations, thousands of major spans are entering their twilight years simultaneously. The challenge is no longer about managing isolated structural issues. It is about addressing a massive, concurrent wave of retirement across entire national assets. Time itself has become the systemic pressure. Delaying bridge maintenance creates a compounding financial deficit known as infrastructure debt. When public agencies postpone routine upkeep, the uncompleted work does not disappear. It accumulates interest in the form of accelerated decay. Data from the Michigan Department of Transportation shows that every dollar invested in early, preventive preservation avoids $6 to $10 in subsequent reconstruction. Despite these clear savings, systematic deferrals have pushed the nationwide bridge rehabilitation backlog to an estimated $125 billion to $191 billion. This multi-billion-dollar backlog represents a growing liability for the transit network. Postponing simple interventions, like sealing deck joints, eventually forces major structural overhauls that require prolonged closures and disruptive traffic detours. Bridges become expensive because they are left untouched for too long, rather than from sudden failures. Under the National Bridge Inspection Standards, inspectors must evaluate every public highway bridge at least once every 2 years. During these reviews, engineers grade the three primary components, the deck, the superstructure, and the substructure, on a scale from 0 to 9. If any single component receives a score of 4 or lower, the bridge is classified as structurally deficient. This designation serves as an asset management tool rather than a warning of imminent collapse. It indicates that a key component has experienced significant wear and requires targeted maintenance. To maintain public safety, transit agencies actively manage these structures by restricting heavy truck traffic, posting lower weight limits, or scheduling repairs while keeping the roadway open to daily traffic. This differs from a functionally obsolete label, which indicates a bridge was built to older design standards, such as having narrow lanes or low clearance, rather than having physical deterioration. When a bridge is restricted or closed, the economic impact immediately spreads far past the structure itself. In modern logistics, reliability is a measurable operational input. For commercial freight, a detour is a direct operational cost rather than a minor inconvenience. Transport data shows that truck operating costs average approximately $2 per hour for every 1,000 pounds of cargo. When a primary crossing is restricted, freight dispatchers must reroute heavy vehicles along longer, secondary roads. These detours add fuel expenses, consume driver hours, and cause missed delivery windows. This disruption quickly affects broader supply chains. Modern manufacturing and retail rely on just-in-time delivery systems designed around predictable transit times. When bridges become unreliable, companies are forced to carry more safety stock to guard against delays, which slows inventory turnover and raises overall operating expenses. This predictability is especially important for industrial hubs and marine ports, where cargo must move continuously to prevent terminal congestion. A single bottleneck at a bridge can stall shipments hundreds of miles away. The impact extends to public safety services as well. For emergency responders, a restricted bridge requires a dispatch route to be recalculated instantly. In a medical crisis or structural fire, detour routes that add even 4 or 5 minutes can change the outcome of an emergency call, turning a routine response into a severe delay. Ultimately, bridge reliability directly shapes regional economic performance. Rather than isolated concrete structures, bridges function as key nodes in a highly synchronized logistics network. When these nodes fail to perform reliably, the resulting delays and added expenses act as a quiet tax on productivity, raising the cost of doing business across entire transport corridors. Physical age is only one factor in structural decline. Today, older bridges operate under far harsher conditions than their designers anticipated. Embedded steel reinforcing bars face ongoing exposure to road salts and moisture, initiating internal corrosion that expands and cracks concrete from within. Seasonal freeze-thaw cycles expand this trapped water, widening those cracks and damaging surface layers. Below the waterline, intense flooding and river currents scour away the riverbed soil, supporting bridge foundations. Above, heavier commercial trucks impose severe physical loads, converting slow, passive aging into an active process of structural wear. Preventive preservation rarely generates the public recognition of a brand new corridor. Because a bridge often appears perfectly functional even as its internal steel corrodes, postponing maintenance is a politically convenient option for agencies operating on tight annual budgeting cycles. Ribbon-cutting ceremonies for high-profile highway expansions offer immediate political capital, while routine deck sealings and joint cleanings occur out of view. This mismatch between short-term fiscal planning and the multi-decade lifespan of heavy infrastructure routinely deprioritizes maintenance. Modern asset management attempts to counter this short-term logic, planning investments across decades rather than election cycles, showing that delay is ultimately a policy choice. The operational vulnerabilities of the transport network are illustrated by 3 specific events. In Baltimore, the loss of the Francis Scott Key Bridge exposed the fragility of a major logistics corridor. In Pittsburgh, the Fern Hollow Bridge collapse showed how local maintenance decisions can escalate into a public crisis. In Minneapolis, the Interstate 35 failure permanently changed public expectations of engineering oversight. While the immediate causes of these events differed, each stems from the same structural challenges. These systems deteriorate slowly over decades, with the most severe failures occurring after years of quiet, unaddressed decline. Today, the temptation remains to fund highly visible new projects. Yet the stability of a modern economy depends on the quiet, unglamorous work of preservation. Until we treat maintenance as an investment rather than a liability, we continue to borrow against our future. Let us know your thoughts below. Every crisis begins as a crack, small enough to ignore until it isn't.